So what are the density? That one you need to calculate. Okay, so this is basically what we have learned in the last lecture. Okay, back to this. We have the EC, we have a EV, EF is somewhere in between. Okay, we also learn about the semiconductor, let's say intrinsic semicon, which is the semiconductor which has no dopant, no impurity to be more accurate. Okay, which means that in this intrinsic semiconductor, you didn't add any extra impurities there. So in this case, your EF Fermi energy level will be equal to EFI, intrinsic Fermi energy level. But if you're adding some impurities inside there, and impurities, then it will become the extrinsic semicon. So after adding the impurities, the EF will no longer be different than the EFI. Okay, it may be deviate from somewhere else. Okay, so today we are going to see how we're going to play around with the semiconductor with the impurities. So let's go back to the slide. Okay, this thing we have already learned that, learned that, done. This one done, this one done. Okay, this one is an intrinsic. Before I forget. Okay, your Ni square is equals to the No multiplied by Po. Okay, also equals to NCMV exponential minus Eg over Kt. But one good thing for you is you don't have to half out all the formula since the test and the examination is the open book. Okay, so this one done. So right now, we need to consider this, the intrinsic Fermi energy level. Okay, let me delete all this thing. Okay, get back to the slide. The Fermi energy level is located near the center of the forbidden band gap energy. What he means that EF, this one EC, EV, EF is somewhere around the middle, but it is not exactly in the middle. So how are we going to determine the Fi, intrinsic Fermi energy level? Okay, we can do some simple mathematics to find where is the location of that. Okay, based on this, at first we know the NO will be always equal to PO in the intrinsic semiconductor. This one is always EC, ESP minus EC, EFI over KT. Okay, as I saying, in the intrinsic Fermi energy, intrinsic semiconductor, EF must be always equal to the EFI. So that's why we can replace it with the EFI equals to EFI over EV divided by KT. Okay, first thing we have this formula. Then we do the logarithm. Okay, we try to log natural logarithm. ESP, but this thing will be gone, we know that. If you are still remember with the mathematics, this will equal to ln MV plus EFI EV over KT. Okay, then we carry here and there. This thing we carry from the other side to the other side. NC will be divided by MV. Or we move this to the other side, same thing. Okay, so this one will become the EFI minus EV over KT minus EC minus EFI over KT. Then we do here. This will become the ln NV over NC. Okay, then we move the KT to the above. So right now, EFI minus EV minus EC plus EFI, because minus multiplied by minus equals to plus. KT ln NV over NC. And then this thing, there are two EFI there. Two EFI equals to the EC plus EV plus KT ln NV over NC. And then I try to divide everything by 2. EFI EC plus EV over 2 plus KT over 2 ln NC NV over NC. And then EFI, this one will be equals to the E mid gap, which means that EC and EV, so in between we draw as a mid gap, plus KT over 2 ln NV NC. Okay, and then EFI minus E mid gap will be equals to KT over 2 ln NC NV over NC. And then this NV and NC, we can further simplify it. KT over 2 ln, don't forget, originally we have a very long formula, 2 pi m n KT over a square 3 over 2 divided by 2 pi mp. Oh, this should be a p, this should be an n at the bottom. KT a square 3 over 2. Then you delete. But you left a 3 over 2 there. 3 over 2 there you can carry forward to the front side. So this will become 3 KT over 4 ln. Eventually, you will get MP over MN. Okay. So this is the formula that shown into here. Any question for this derivation? One thing good for you is you don't have to remember this, how to derive it, but you need to know how to use it. For us to know how to use it, normally we will be given some of the situation like this. Okay, let me delete all this. Okay, so for example, calculate the position of the Fermi energy, intrinsic Fermi energy, EFI, with respect to the band gap, EM gap. Then he gives you the effective high density carrier mass R, this one Mn equal 1.08 mO, and P equals 0.56 mO. Okay, we know that this one is equals to 3 over 4 KT ln MP over Mn. 3 over 4. What is KT? KT we know, T is 300. So we know that this is equal to 0.005259. 0.0259 EV. And the EV form. Then you run 1.08, 0.56 mO divided by 1.08 mO. From here, you can simply calculate out the answer. Okay, so far, any question? Tak ada? Boleh faham tak? Boleh? Okay. So since you can understand this, so let us try to understand what is the extrinsic semiconductor. So as I mentioned that if you are adding some extra impurities, no matter it's extra electron or extra holes, it will cause the intrinsic semiconductor to become the extrinsic semiconductor. The process of adding the impurities, we call it as a doping. Okay, just for example, in this diagram, mostly are in the silicon, but you are adding the phosphorus. So the phosphorus are the doping process, the adding process. So why are we going to need this? So for example, originally your conduction band is here, UV is here. Let's say if you are trying to add some dopant. Whenever when we are talking about dopant, we are adding electrons, extra electrons inside there. How are we going to add the extra electrons? We add one donor state here, ED. This one is the donor state energy. And this state will be full with the electron. Okay? Then after the adding the electron, all the electron will be jumping from this ED state to the conduction band. Okay, originally the electron is here, but somehow you add the extra electron here, which means that right now you are going to have more electron than the proton. Okay, last time we mentioned that one electron, when you create one electron here, you will create one hole here. But you are adding the extra electron without creating the extra hole. So that's why right now your E is more than the hole. And this will become the dopant. Sorry, this will become the N-type semiconductor. Why N-type? Because we are adding the extra electrons. Okay, like the one that mentioned here, donor impurity atoms add the electron to the conduction band without creating hole. Okay, so this will become the N-type semiconductor. Same thing happened to the this one. If you want to add the to acceptance, okay, we are trying to add the acceptor. Acceptor means that we are trying to create the one state of the acceptor energy. Okay, here got a lot of the hole. And this hole is for all the electron to jump to here. Okay, so right now you can create more extra hole here. Alright, originally all are full with a hole only. Right now you're trying to create more hole here. So this one, if you are having the other way around, hole more than the electron, this will become the P-type semiconductor. Okay, this part, can you understand? Boleh faham tak? This one. Okay, Lau Lục Jing say okay. What about the rest? Brenda, what do you think? Can you understand this? Chu Zhang Heng, what about you? Ernest Ng Hang Xiang. Okay. Okay, let's continue. So this one is the extrinsic semiconductor, as I mentioned. Adding the extra donor or the acceptors will change the Fermi energy level. Before you adding any extra dopant, your E will be equal to EFI, intrinsic Fermi energy level. But after you're adding the dopant or the acceptor, your EF will no longer equal to the EFI. It will deviate from the EFI because you change the characteristic right now. How is it going to change? Okay, so let's say if your EF is more than the EFI. For example, this diagram, you see EV, EFI somewhere around here, and your EF somewhere around here. If your EF is more than the EFI, which means your NO must be more than the PO. NO more than the PO, which means the electron will be more than the proton or the hole. Then the NO will become the majority carrier because NO more than PO ma. This one common sense, right? Then hole will become the minority. Okay, and this is the n-type semiconductor. So diagram wise, last time we learned about this diagram already. But somehow you can see that if after adding the, let's say the dopant, this area will be larger than this area. This area represents the whole concentration. Right now the area is larger than the whole one. So that's why this is the n-type semiconductor. The other way around, if this is the whole, this EF will be less than the EFI. So if this is the extra adding here, somehow EF is less than the EFI. EFI more than EF, PO more than NO. Then this thing will become the majority is the whole. Then majority is a whole as mentioned here. Minority is the electron. Then this thing we call it as the p-type semiconductor. This area will be bigger than this area. Okay, let's go to the formula wise. How are we going to play around with the formula wise? Can we include the EF and the EFI in our formula? Yes, we can do that. But how are we going to do this? So let's see. So we come back to our original formula. NO is equals to the NC exponential EC minus EF over KT. Okay, this formula we have tried to play around sometimes last lecture and also the tutorial class. Then we try to expand the formula. ESP EC minus EF over KT. Then this can be equal to plus EFI minus EFI over KT. This one is a plus, plus. Okay, then we try to integrate both together. NC ESP. Then, okay, EFI. We use the EC minus EFI first. Over KT. And then we try to plus the EF minus EFI over KT. We try to rearrange everything. Okay, if you want to break it, you can see minus EC plus EF, then plus EF I minus EFI. We try to combine these two together. Let me see. Or you can change it to minus or you can, no problem, I believe. Okay, so this thing, okay, this thing combined together, these two things combined together, no problem, also can. Okay. Okay, so this formula, we can simply break it into EC minus EFI over KT, then exponential EF minus EFI over KT. Okay, so we know that Ni will be equals to the NO will be equals to the PO also. So we can assume that this part will be equals to the Ni. Okay. And we can further simplify the formula into the NO will be equal to the NI exponential EF minus EFI over KT. Then PO will be equal to the NI exponential. This one is the EFI minus EF over KT. So this is a two formula for the extrinsic semiconductor. Okay, so here we are making some of the assumption. Last time during the very first lecture, we know that the Ni will be equals to the No will be equals to the PO also. Okay, then NO will be equals to the NC exponential minus EC minus EF over KT. PO will be equals to the MV ESB EF minus EV over KT. Okay, so that's why we are trying to equal Ni to this formula. Then we replace somewhere inside here. So that's why we get this formula. But this is for the extrinsic semiconductor only. So sometimes the question will be given you the EF, or maybe given you the EFI, or maybe given you the Ni. Then he asks you to calculate the NO. So you're going to use this formula to calculate it. Last time we tend to calculate using the EG, right? Maybe EC minus EV, EF over KT. We use this. Then we use the NC. But sometimes question will give you this info. Then use all this info to calculate the hole concentration or maybe the electron concentration. So this is the other concept. Okay, let's continue. Okay, so same thing. If your EF more than the EFI and O more than the NI, then this one is equals to N times semiconductor, P times semiconductor. Then multiply together, become the Ni squared, nothing much. Okay. So, as a conclusion, you can see this diagram. Okay, let me summarize everything here. My pen here. So NO is the electron concentration in the conduction band. Okay, EC, EV. NO is somewhere between here. PO somewhere between here. Okay. Ni square equals to the NO multiplied by PO. EFI, Fermi energy level. Without any impurities, Ni equals to the NO equals to the PO. Everything are equilibrium, all ngang. Then your EFI will be equals to EF. Then if in this case extrinsic, your NO will not be equals to the Ni because everything will be changed. You add the extra thing inside there. Then your EFI is not equal to EF. It will be changed. Depends on whether it's a N type or P type. Formula wise, okay, these two formula we have used multiple times. When you multiply both together, will become Ni squared. Then this is the derivation that we have done just now. Extrinsic semiconductor, you have the EF and the EFI, and your NO will be changed. When your NO is more than the PO, N type, PO less than the NO, P type. Okay, so this is what we have learned so far. Any question for this lecture? Any question? If no, maybe today we can end the class slightly earlier. Okay? It's very hardly to have this happen. Very hardly to have this happen for the semiconductor. Okay, if no question, then we end the class for today. Thank you very much for the attention and have a nice day. Have a nice weekend. Enjoy weekend. Don't go out. Right now it's already 15K cases. 12K, sorry, not 15K. Okay? So I think that's all. Bye everyone. Enjoy your day. Enjoy your weekend. Then go out. 12K cases. Okay. Bye everyone.